Currently, our code for elliptic curves works for small primes p, but in real-world cryptography, the primes are extremely large, and our approach currently is not going to work. In this video, we're going to adjust our code in order to do computations on real-world elliptic curves recommended by NIST. Alright, the code that we wrote before works pretty well. We are able to print out the points on an elliptic curve, and we're able to calculate the group law, the addition between two given points. But it's important to note that this code is only going to work for small primes. Once the prime starts to get large, this code is going to slow down more and more to the point where it's not even usable. And we would eventually like to do some examples where we deal with a real-world type of elliptic curve. That's, in other words, one that's recommended by NIST. And these elliptic curves have very large primes, p, associated to them. So our code in its current state will not work for any type of real-world elliptic curve. To get an idea of how large the parameters are for these curves, we can look at this document here, this PDF, and if we go to page 12 of the document, which I think is page 22 of the PDF, we see the parameters associated to a very specific elliptic curve, which they call P224. The prime P is defined as this value. Notice it's originally 2 to the power of 224 minus 2 to the 96 plus 1, and that expands out to that base 10 value. And then A is -3, which means it's 3 less than P. B is that number. And N given here is the number of points on that elliptic curve. So they tell us all of these values. And this defines a specific elliptic curve. The first thing to correct in our code is that we cannot write for loops over the prime P anymore. Of course, when P is a small value, you can do for loops over it, but the prime we're trying to use right now is so large that any for loop over all values from 0 to P minus 1 is going to take an unreasonable amount of time, right? So even with a supercomputer or whatever. So we cannot write this style of code anymore for the primes that we're interested in using. And another big problem is we cannot store all the points of this elliptic curve in a list. When the prime is small, yeah, you can do that. But once the prime gets to be large, like on these NIST curves, there is no way that we can store all the points in a list. And just to clearly see why that is, let's think about that for a sec. If we wanted to store all the points of P224 in a list, how much space would that take? Well, the prime P there, by its very definition, you can see it's 224 bits, right? If P was just 2 to the 224, it'd be 225 bits, but then we're subtracting a little bit off here, so it's 224 bits, which is why the elliptic curve has that name, right? So any point on the elliptic curve will have an X and a Y value, so that'll be a total of 448 bits for every point. If we multiply that by n, the number of points on the curve, and then divide it by 8 to change to bytes, we see that to store all the points of this curve would require 1.5 times 10 to the 69 bytes. If we search for how much data there is in the world in 2020, we get an answer of 40 zettabytes. That's a theoretical approximation, but it'll serve our purposes here. If we convert 40 zettabytes to bytes, we see it's 4 times 10 to the 22 bytes of data in the world. So right away we see the problem now. All the data in the world is 4 times 10 to the 22 bytes, and all points on our elliptic curve is 1.5 times 10 to the 69 bytes, incomparably more than all the data in the world, right? So we have no hope of pre-computing all the points of a real-world elliptic curve and storing them in any type of medium. That's not going to happen. So we need a different approach. So how do we adjust our code to make things work on a NIST curve? The good news actually is that we can do it. We can make some adjustments to our current code, and we will be able to do computations on these real-world curves. One thing we definitely have to do, like we said, is get rid of any for loops over p or any large values, and the current method of storing all the points of the curve in a list, that has to be scrapped. We need a new approach. The first thing we can address to fix in our code is with the inverse mod p function. So currently, the way we're finding the inverse of an element in fp is just to do a brute force search over all y values. And like we're saying, this is no good anymore. We can't do a brute force search over such a large value of p. The solution for that is Fermat's little theorem. Recall that if you have a prime p and any value of positive integer x, which is relatively prime to p, then x to the power of p minus 1 is congruent to 1 mod p. And if you break that up, x to the p minus 1 is x times x to the p minus 2, you see that the multiplicative inverse of x is x to the p minus 2. So that's a corollary of Fermat's little theorem, that if you have a prime p and any positive integer x which is relatively prime to p, the inverse of x is given by this formula. It's x to the power of p minus 2 mod p. And if we use this idea to rewrite our inverse mod p function, then we just say that if p divides into x, we'll return none because there's no inverse in that case. But otherwise, the inverse, we can use the POW function, modular exponentiation, and we return x to the power of p minus 2 mod p. And the good news is modular exponentiation is fast, even if p is very large. So, and another good news is the addition function, that can remain unchanged. That, as our previous code, we'll just copy and paste that in. As long as the inverse mod p function is fixed, as we just discussed, then this addition function can just be copied right over directly. No changes are necessary. But we have big problems with our function define points, and we know why. The two loops there over the for loops over p are no good because p is too large now. And when we try to store all these points in a list, we know that that is just not possible because there's just way too many points now to store. Well, first we definitely need to get rid of the idea of storing all points, and the solution is interesting. Instead of storing all the points, we're just going to store one point, and that's called the base point, also called the generator point. And it's not unique. There's lots of generator points, lots of base points, but we fix one. And then the idea is every point on the curve can be found as a multiple of the base point. And whenever we're given a curve to use from the real world, a base point will be specified for us to use. And what does it mean? What does it mean to be a base point? A point G is a base point of an elliptic curve if every point on the curve is the form k times g for some integer k, where k is between 0 and n. It's okay if k is 0, but k is strictly less than n. And moreover, the value of k is unique. So every point on the elliptic curve is a unique multiple of the generator. And when we write kg, let's just make sure we understand what we mean by that. If k is 0, 0 times g is just the infinity point. And when k is greater than or equal to 1, so k is a positive integer, all kg means is to add g to itself k times. And that returns some point on the elliptic curve. An important little property that the base point has is that if you take the base point and you do its nth multiple, where n is the number of points in the group, then you get the identity value, which is written as infinity here, the infinity point of the elliptic curve, which is just the zero of the curve. And this just follows from a general result in finite group theory, that if you take any finite group of order n, the nth power or nth multiple of any element is the identity. And this theorem also implies Fermat's little theorem when you apply to the group of FP cross, but let's not get into that. So the base point of P224 is given to us in the document there. It's the point G. It has an x and a y value. It's a point on the curve, and here are the very large numbers that each x and y are. And so this means every point on the curve P224 has the form kg, where G is, where k is some value between 0 and n, including 0 but not n. If we did n times g, we would get the infinity point, the 0. Now, we need to think about how do we find multiples of a point in code. So let's let p be any point on the elliptic curve, and let's imagine k is some positive integer. And we want to find a way to calculate kp, which means p added to itself k times. Now, if we just use the definition of kp, we might write some code like this. Just define q to be 0, like the infinity point, and then just do a little loop, the number of times that k is, and just add p onto kind of like a tally. Think of q as a tally, and each time we go through the loop, we add a p onto it. And we do that the number of times k is. And that's pretty clear that that represents adding p to itself k times, and we return that value. But there's a problem with this code, right? Because since k is between 0 and n, k may be very close to n, and n is extremely large, so k may be very large as well. And if k is very large, we can't do a for loop over k. That's not going to work. So there is a very nice algorithm to calculate multiples of a point, and it actually involves the binary expansion of k, the base 2 expansion, and the number of bits of k is logarithmic in the size of k, and that's why this algorithm is going to be very fast, even for very large values of k. All right, so here's a brief description of the algorithm. Let's write k in its binary form, so as powers of 2, the summation from bi 2 to the I, where each bi is either 0 or 1. Then kp can be written as a sum as well. Kp would be the sum over I of bi 2 to the I times p. Now, why don't we just abbreviate 2 to the I p as xi, and then we can just rewrite it as kp is the sum over I of bixi. Now the thing is, bi is just 0 or 1, so if bi is 0, then bixi is just 0 as well, and we can ignore it. And when bi is 1, then bixi is just xi. So kp would just be the summation of the xi over which values of I? Those values of I which have a bit value of 1 in the expansion of b. So that last formula there is the main idea. Kp is the summation of these xi's, where I ranges over the bit values of b, which are 1. And the xi's, which are originally defined up here as 2 to the I times p, you can easily see that we can get a recursive formula for xi like this. Define x0 to be p, and then for I greater than 0, just define xi to be the double of the previous one, so 2 times xi minus 1, which is just xi minus 1 plus xi minus 1. And that gives a nice recursive definition of the xi, and using those two ideas there, we can easily write a formula for kp. So let's check that out. So given k and p, K is a positive integer, or K is 0. P is some point on the elliptic curve. We define X to be P. That's kind of like X0 equals P. And then Q is the infinity point, which is like 0. Now, if K is 0, just return the infinity point. Otherwise, we know K is non-zero, and we're going to cycle through the bits of K. And each time we cycle, we access the least significant bit by doing K and 1. If that bit is non-zero, in other words, it's equal to 1, then on Q, we add X to it. And I'll go back here. You notice at the bottom there, the summation over the Xi. That's exactly what we're doing on line 8 here, when we do Q equals the addition of Q plus X. And then X, no matter what, X though is added to itself. It's doubled. That's the Xi equals Xi minus 1 plus Xi minus 1. And then all the bits of K on line 10 are shifted to the right by 1, so that in the next cycle of the while loop, we access the next least significant bit. And then at the end of that loop, when K is 0 eventually, the value of Q will be the multiple K times P. Now we can make a little simplification of the code here. Instead of using X, we could just reuse P. Notice how we don't use P after the very beginning. Why don't we just use P in place of X, and we'll just make it a little bit shorter. So that's our code for multiples. Usually we take the point P to be a generator point G, but the code works for any point P on the elliptic curve. All right, so we're ready to implement these ideas in Python now. And we'll start from an empty file, but we'll copy paste some of the snippets of our previous code in. We'll start by defining our infinity point to be the Python constant none. It's probably not the best way of doing it, but it's good enough for us. We'll call our class elliptic curve again, and we'll define the constructor. It's going to take in 3 parameters, the prime P, and the A and the B values, and the value of self as well. And then we'll just define, we'll set those internal values, self.p equals P, self.a equals A, self.b equals B. So that's kind of the same as before. Now if you remember, we had some helper functions. One of them was reduce mod P, and the other was equal mod P. Those 2 functions, we can just copy and paste those over. Those remain unchanged. But remember, we talked about inverse mod P and how we had to change that. We have to use Fermat's little theorem there. So we'll write that code now. If we're given a value of X, such that when we reduce it mod P, we get 0, that just means P is divisible by... That means X is divisible by P, and so X doesn't have an inverse mod P. So we return none in that case. Otherwise, we use the Python function POW, and we calculate X to the power of P minus 2 mod P. And like we talked about, that is the multiplicative inverse of X mod P. I think instead of P minus 2 there, we could even just write -1. The POW function would accept -1 as the second argument in this case. But we'll just write P minus 2 because we understand the reason why that works through the corollary to Fermat's little theorem. And then, like we said, we could just copy paste the addition function back in from last time, so that's nice. We don't need to change that at all. But the main function that's new for us right now is this multiple function. So if we have given a value of K and P, K is a positive integer or 0, and P is a point on the elliptic curve, we need to code a function that returns the multiple KP, which just means P added to itself K times. And like we talked about in the slides, the way we do that is we define Q to be the identity element of the group, the infinity point in other words. And if K is 0, then we just return the infinity point. Otherwise, while k is non-zero, we cycle through the bits of k, and each cycle through the loop, we access the least significant bit. We do that by doing k and 1. If that bit is not 0, in other words, it's 1, then onto q, we add on the point p. And each time p is doubled. So p is p plus p, and then k is bit shifted to the right by 1. And then at the end, after the k becomes 0, q will be the value of kp, and we return it. And that's how that works. Why don't we just make a little function that tells us if a given point is on the curve or not? So let's define is point on curve. Its given values x and y. And then we just want to see if y squared is equal to x cubed plus ax plus b mod p, which is just another way of saying x comma y is on the elliptic curve. So we actually, that's all we need, believe it or not. Let's try to work with this elliptic curve P224. So outside of the class, let's define P to be that large prime given in a document. A is -3, B is that value, and P224 is the elliptic curve with those parameters. So we instantiate an instance of that class. And in that document, we also talked about the generator point, gx and gy. Now, at minimum, that point better be on the elliptic curve, right? We should check that. Let's see if the point gx, gy that they give us is on the elliptic curve. It better be. And we can test that using the little function we just wrote, right? And when we run it, we see that the result is true. So yes, this point is on the curve. That's good. Now, why don't we call G to be the point gx comma gy, the tuple. And as a first little test of our code, let's find the multiple of 1 in G. So we just do 1 multiplied by G. That should give us G, right? So Q should equal to G. Let's print that off, and we see, yes, that's true. Good. Now, we're told the order of this group. N is this unbelievably large number. And Q, why don't we define Q as G to the power of N minus 1? That should just be some random point on the curve, right? When we print it off, we should just get some very large numbers, and we do. Why don't we test if this point is actually on the curve? It better be, right? When we test it, we have to print out the value, and we see it is on the curve. Good. Now we come to the exciting part. If we calculate the nth multiple of the generator point G, what should we get? We should get the identity element. In other words, the infinity point. So let's test that. Let's define Q to be the nth multiple of the generator point. And let's print off whether Q is equal to the infinity point or not. And we get true. So great. So that's actually very cool. And that's as far as I wanted to go for this video. Thanks for watching.